Hello. Before we delve into the details of individual topics in physics, it's useful to have an overview of the subject so we know what it is that we're working towards. So what is physics actually about? Well, as with all sciences, physics is about describing some set of features of the world around us. So we've got an emphasis there on description. And in the case of physics, we're trying to describe the most fundamental features of the universe. These are the features that are applicable everywhere, at all locations and at all times. And we want our descriptions to be as fundamental as possible as well. We don't want to be breaking them down into sub-descriptions. We want to go right down to the root of things. So what are these features then? So if you think of the universe as being a container of stuff, and that stuff interacts with itself in different ways, then that gives us 6 topics. The container we can describe in terms of space and time. Everything in the universe exists in space and it changes across time. So we need descriptions of those. And then all the stuff that's in the universe is matter and energy. There isn't anything else there. So we need descriptions of those. We need to say what matter and energy are, what they're made of, how they stick together, how they move around, how they interact. How do we get all of these different types of stuff that's around us just from these 2 things, matter and energy? So we're trying to describe those. Those interactions between matter and energy we can describe, at least initially, in terms of force. And then that gives rise to motion, which is matter and energy moving around. So that's 6 topics that we've got there. We've got space and time, which is the container of the universe. We've got matter and energy, which is the stuff in the container. And then we've got forces and motion, which is the behavior of the stuff that's in the container. So that gives us our 6 topics to get us started. Once we described all of those, these descriptions, they've got 2 main uses. One is just great to be able to describe all of this stuff because it's really interesting. Who wouldn't want to know how the universe works? There is value in just knowing, but there's also value in being able to use it to make predictions. If we can describe space, time, matter, energy, force, and motion, then we can predict how things will behave in different circumstances. And that is really useful. And it can take us into the realms of engineering as well. Because if we can say, oh, in this situation, that will happen, then as an engineer, we can say, well, how can we change the situation in order to get a better outcome? So there's a lot of uses for what we're doing in physics. So how do we get these descriptions? Well, more to the point, how do we create accurate descriptions? Anyone can go out and start making descriptions of the world, but as we know from history, previous descriptions of the world have included things like flat Earth and the sun going round the Earth and things like that. So we don't want any old description, we want accurate descriptions. Well, the first thing for any description is we need to make observations. Science is not mathematics. In mathematics, when you're learning about, squares at school, you don't need to go out and find a whole load of squares. You can say, oh yeah, a square is, it's got 4 sides, 4 corners, all the sides are the same length. And then off of that, you can come up with a whole load of interesting things about squares. You don't need to go and look at them. Science isn't like that. So with physics being a science, we need to go out and look at the world because the world could be different. We don't know until we look at it. As already mentioned, we're not that great at looking at the world in an unbiased fashion. So we need a particular way through scientific experiments to do controlled observations of the world. So we don't want to be biased. We need to try and strip all of that out and actually see what's going on. So we need to be able to do experiments. Off of the back of these controlled experiments, we can then discover laws and theories. So a law is a relationship between 2 things. So it's saying if this happens, then that will happen. It's a straight description. Quite often we can write as a formula. We can codify it into mathematics, and we can use that to describe how one thing changes according to something else changing. Now, those laws don't tell us why stuff happens. So that's where theories come in. And a good theory will bring together a whole load of laws and give an explanation for the behavior. So as an example, we might go out and, I don't know, fire a whole load of tennis balls up in the air, and we could get a relationship between the speed at which we fire them up in the air and the height that they reach. And we could create a law between speed and maximum height. And we could write that down as a mathematical formula and say, right, great, we got a relationship. If we fire at that speed, then it will go to that height. That's our law. But it's not telling us why. We need a theory. We're going to need something to do with gravity. We need a description there. And our theory will then say, oh, yeah, well, because of gravity and the force of attraction between the Earth and the tennis ball, this is giving us then a more detailed description of what's actually going on. So the laws are really useful because they really help us to predict things. They'll say, well, if this has happened, then this is what's going to happen as a consequence. But the theory is then bringing these laws together and giving us a much more detailed and richer explanation of what's going on. So we're discovering these laws and theories through experiments, but we're also wanting to improve the ones that we've already got. We need to keep looking for better descriptions because, as I've already said, quite often our descriptions are wrong. You think something's correct for ages, and then someone goes out and observes something and finds out, well, actually, that doesn't fit with the law or the theory. We're going to need to change our description in order to explain what we've just observed. So we have to keep being on the lookout for better descriptions. And this brings us on to a very, very important thing that often confuses people when they're learning physics, is just because you find something that breaks a law or a theory, and then a new theory is developed, which is more accurate, that doesn't necessarily mean that the old theory is useless. Quite often the old theory, particularly if it's been around for a long time, is very good at describing stuff in particular circumstances. So as an example, as we're going to see a lot of, Sir Isaac Newton, back in the 17th century, he came up with a whole load of descriptions of how things move and interact, which subsequently, about 100 years ago, Einstein showed, yeah, well, actually, they're not as accurate as we thought they were. But people have been using Newton's laws for centuries, and they were very accurate, and they still are in a lot of circumstances, and we can still use them. We don't have to go to Einstein's theories and use those. We can still use what Newton described. It's still useful. So we've got two descriptions then of the same thing. One of them's more accurate, but we don't always want that one. Sometimes we want to use the one that's good enough, it's accurate enough, but it's easier to use and it's easier to learn. So we don't always throw out the old description. So this is something we really, really need to keep in mind all the way through learning physics, is we will often use more than one description of the same thing. But that doesn't mean to say it's wrong because we've got two descriptions. We can have two different descriptions and they're both useful. Right, so how do we then become a physicist off of the back of all of this? Well, we need to learn what descriptions already exist. We're not going out there and trying to rediscover everything. There's hundreds of years of people coming up with descriptions. So we're going to learn the best ones and how to apply them. We need to learn to conduct experiments, as already described. being able to conduct scientific experiments is crucial to being able to discover accurate descriptions of the world. And then we need to learn the language of physics. So that's primarily mathematics. But then nowadays you need ideally to be able to do coding, so you can develop computer programs to do analysis. You need to be able to write well and speak well, so you can communicate ideas. So all of these will be present throughout the videos that I'm doing, but I'll also create separate playlists that will focus on these 4 topics to see how we can specifically improve our maths, our coding, our writing, and our speaking. So that's a quick overview of what's going on in physics, and we can use that to guide our learning over the coming videos.